Hello everyone. In this lecture, we will learn about the concepts of phasors and how that is used in AC circuit analysis. So let us start. Now first, the concept of phasors actually was originated from this version of Euler's formula. This is particularly called the complex representation of Euler's formula. And how this thing is derived, if you want to understand, you can go through the video of jHan. I have added the video link in the description, and he has clearly explained how this actually is derived. But for now, in this lecture, we want to visualize how this complex number can be represented in a complex plane. So this e to the power I theta is obviously a complex number. This is the real portion, this is the imaginary portion, and here in the right we have drawn a complex plane. Horizontal axis is the real one and the vertical one is the imaginary axis, and in the original equation we have just added a modulus here r, so it will be added with the real portion also with the imaginary portion. So in that case, the length here, the horizontal length is r cos theta and the vertical length is r sin theta, right? And the length here in the polar form, this is r, and the angle with the horizontal axis is theta, right? Then the value we are getting at this point is r e to the power I theta. Now in our domain, I mean electrical engineering domain, we actually represent the whole thing in a quite different manner. The first thing is we are never going to use I for representing imaginary number. We are going to use j instead of I, and here this exponential form of Euler's formula, this thing can be represented in three forms, right? This is the exponential form we have already seen. This thing can also be represented in terms of polar form, which is r and the angle is theta. And in the figure we have already explained that this length is r and this angle is theta, and the whole thing also can be represented in terms of rectangular form. If I just take this length here, you know, as x and this length here as y, then it can also be represented as x plus jy. And we can also take the traditional approaches of converting a rectangular form into a polar form or a polar form into a rectangular form using this kind of equations here. Now the most important thing here to understand is, what if this value theta here, this is changing with respect to time. Let us say if theta is time, then obviously it will progress further with as the time progresses, right? Then how this total figure should look like? Can we understand that? To understand that, let us look at a 3D representation of our Euler's formula. Now here in this graph, you are actually seeing the 3D representation of our Euler's formula. Here the parameter theta that we saw earlier, it is taken as t. It will obviously increase with respect to time. As a result, we are seeing some changes. So let us try to understand. Now here, you see this rectangle with gray color. This is actually our complex plane. The vertical axis is our imaginary axis. The horizontal one is the real axis. So as the value of t is increasing, obviously it is spirally going forward in time. Our complex exponential e to the power it, this is actually going forward with respect to time. And the blue line, the blue spiral we are seeing, this is representing the value e to the power it. Now this thing has two portions, right? One of them is the real portion, another one is the imaginary portion. So if we want to visualize the real portion as well as the imaginary portion, what we have to do? We have to take the projection in each direction. So if we want to see the real portion, then what we have to do? We have to actually take the projection from top or bottom. Then we are going to see what is happening in the horizontal axis, and that is drawn in this green line, right? And if we want to see the imaginary portion, then we have to take the projection from this direction, I mean the left or the right direction, and that projection is shown here in this red sinusoidal. So it is producing two different sinusoidals, and they are 90 degree apart with respect to each other, obviously, because cos t is 90 degree apart from sin t. But in this way we can actually represent the real portion as well as the imaginary portion here. So as you can see, both of the projections are showing spirally our e to the power it is progressing in the vertical direction. If we take the projection, we are going to see the green one, which is the real portion of our e to the power it, and in this direction we are going to see the red one, which is red sinusoidal, is actually the imaginary portion of our complex exponential. Now this visualization will help us a lot later on when we actually go on to the concepts of phasor. Now most of the calculations in AC circuit will involve complex number, so we need to understand what are the basic operations allowed. I think these things were already covered in your intermediate level, but still let us look at those things to understand and to remember. Now if we have three different complex numbers, something like this, j, j1 and j2, all of them are represented both in rectangular form as well as polar form, then these are the operations allowed generally. And most of the operations are very easy to understand, but let us look at this one. This is very important for our case. Now if we want to multiply two complex numbers, j1 and j2, then we can first of all represent those in terms of polar form. Then multiplication will be basically multiplication of the modulus r1 and r2 and the addition of two arguments theta 1 and theta 2. So you see, in the argument portion the multiplication becomes addition. This is a very important characteristics of complex numbers. And another thing I want to emphasize how these things are actually represented in complex domain. So we already know the value of j, or previously as we had known, the value of I is equal to root over minus 1, right? Now if we want to represent 1, the value of 1 in this particular graph here, then we can just take it here and call that 1. Okay, that will be possible only if the length here is 1. We are taking the length as 1. Now if we multiply this 1 with j, okay, 1 with j, then what will happen? To understand, let us first plot the value of minus 1. If we want to plot the value of minus 1 in this complex plane, that will be this one, right? This is minus 1. And to get to minus 1, we had to go in total 180 degree, right? Now what is j? If we multiply j with itself, I mean j square, that is equal to minus 1. So for minus 1 we had to go 180 degree in the counterclockwise direction. To get to j, that is 1 multiplied with j is equal to j, we have to go half of that, half of 180 degree. So that should be something like this. So it should be 90 degree. And we can draw it here. This is the value of j. And after multiplying this j with again another j, we are going to get j square, or is equal to minus 1, which is this one, right? And again if we multiply this thing j square with another j, we are going to get j cube, or also we can say minus j, because this value is equal to minus 1, so minus j, and that value will be this one, again 90 degree in the counterclockwise direction. So this is minus j or j cube. And after that, if we again multiply it with another j, j multiply with j cube, that is equal to j to the power 4, and that is in fact 1. So j to the power 4 is equal to 1. In this way, as we multiply with j, we go 90 degree in the counterclockwise direction. Now, can we actually prove this one based on that? To prove that, we can just write 1 divided by j, which can be written as j cube divided by j to the power 4, and j cube is equal to minus j, as we had earlier seen this one, right? And j to the power 4 is equal to 1, so we can write something like this. So we can write 1 by j is equal to minus j, and this particular expression is very important for our case. We will use that throughout our calculation in AC circuit analysis. Now let us start with the concept of phasor. So here, as you can see, this is the complex representation of Euler's formula, or we can also say this is complex exponential. Now for this complex exponential, we have two different portions. One of them is real portion, the cos theta, and this portion is the imaginary portion. So we can actually represent cos theta as the real portion of complex exponential and sin theta as imaginary portion of complex exponential. This can be written, and we are going to use this concept right now to represent the phasor. How is that? So let us say in a circuit we want to use this AC signal or AC source V of t, which is Vm cos omega t plus phi. We have seen this kind of signals previously in our previous video. Here we have one added term, which is the phase. So our signals can have different amplitude, different frequency, as well as different phase. Now can we actually represent this AC signal in terms of a complex exponential? Is that possible? To do that, let us look at this equation right here. So we have just modified the complex exponential so that we get this expression. Now here the real portion of this complex exponential looks exactly like our V of t, and there is another imaginary portion, and the real portion is Vm cos omega t plus phi. So we can write V of t is equal to real of this complex exponential, which is Vm e to the power j omega t plus phi. And another thing we can do is, from our previous knowledge, we know that if we have e to the power x plus y, we can represent that in terms of e to the power x multiplied with e to the power y. This is possible. So using that concept, we can just simplify this portion into this one. We have separated the phi portion from omega t portion. Now this thing here, this particular portion is actually the phasor of our signal V of t. Okay, so as you can see here, this is our sinusoid, which we want to represent in terms of complex exponential. And what we have done, we have taken the real portion of our total complex exponential, and this portion here, this one, without the time factor here, can be called the phasor, and e to the power j omega t is the time factor here. Okay, so we will have phasor as well as time factor in here, but the benefit is now we can separate the phase portion from the time factor. Previously, in the previous video, I said that one of the problems we face solving AC circuits is that we cannot separate this time portion, and as this value is changing with respect to time, solving AC circuits is very difficult. We have to deal with differential equations, and here we have somehow separated the time portion. This is the benefit we are going to get. And now let us try to visualize this phasor representation using a complex plane graph. Now here in this graph you can see the phasor representation of a complex exponential. The left portion here, this is just a complex plane. We have rotated this one 90 degree counterclockwise, so that in the vertical direction we have real axis, and in the horizontal axis we have the imaginary axis. This is just for convenience, so that we can represent the phasor in this direction. So what is happening? We know we are taking the real portion of this whole signal, right? And this point here, this is representing the complex exponential, which is this one, right? Vm e to the power j phi e to the power j omega t. And we are taking the real portion of that. So what we have to do, we have to take the projection in this direction, right? So if we take the projection in this direction, we are going to see this graph here, which is the phasor of this complex exponential. And here, if we take t is equal to 0, then what will happen? In this particular equation, we will have t is equal to 0. E to the power j omega t, this value should be equal to 1, because e to the power 0 is equal to 1. So kind of we have vanished this particular portion. What we are left with is just the amplitude and the phase. And that is what we are seeing here. We have this value of angle, which is the phase of our signal, and this amplitude here is the Vm, the amplitude of our signal. And as a result, we can also take the projection in this direction to see this wave shape. And this is for t is equal to 0. In real life, t will go forward in time, so that should be looking something like this. So this particular point will move in the counterclockwise direction with the speed omega, the angular speed of our signal, right? And that is what we are seeing here. And this is the actual sinusoidal graph we are going to generate from this complex exponential. Now here, even though the graph is actually moving in the left direction, the point which is representing our signal, which is this one, right? This particular point, this is moving forward. If you consider this signal, this particular graph to be static, right? Then obviously this point is moving forward in time. And that is what happening. The signal is moving forward with respect to time as the time progresses. And that is what we are seeing here. Now the thing I want to emphasize is that for our phasor domain representation, we always take t is equal to 0 so that we can omit the value of e to the power j omega t as 1, so that this value will be omitted. Finally, we are just left with this value, Vm e to the power j phi. Right, and that will actually make our calculation easier, because we don't have any time portion. We don't have to worry about that. After doing all the calculation, we can again put the time factor portion to get the value of actual v of t. That is what we are going to do. So as we had seen in the graph, we can say that the phasor may be regarded as a mathematical equivalent of a sinusoid with the time dependence dropped. So we are just omitting this time portion or time factor by putting t is equal to 0 somehow, and that is what written here. The value of the sinusoid v of t at time t is equal to 0 is the phasor v of that sinusoid. Okay, so we are just taking the value t is equal to 0, then we are going to get phasor, which is this one, right? Without this portion, this is the value we are getting, and this is the phasor of that sinusoid v of t. And as you can see, this particular portion here, which can also be represented in terms of polar form, this is the amplitude, this is the phase, and as it has two values, magnitude and phase, phase can be regarded as the direction, so it can be considered as a vector, and we represent this phasor as a vector. That's why we have used this bold font here. We are always going to use bold font when we represent a phasor of a sinusoid. So we can summarize the whole discussion using this representation. So initially, when we have a circuit, we will have different signals. In the time domain representation, we are going to convert those into their phasor domain form like this, just by omitting our time factor. Here we have this time factor. We can just omit those to get our phasor domain representation, and we will do all the calculations in phasor domain. After all the calculations are done, we are again required to move to our time domain representation. So what we will do, we will again just put our time factor here so that we get the time domain representation. So this is the general process we are going to follow when we want to solve any AC circuits. Now if we understand phasors, then this particular thing here, this is the phasor diagram. So we can always represent each of the phasors in this diagram. This is just a simple complex plane. This is the real axis, this is the imaginary axis, and all the vectors or all the phasors we get for all the sinusoids we have in the circuit, we can represent those here using a vector, because all of the signals will have some amplitude as well as some phase with respect to our horizontal axis. So if we want to represent Vm angle theta, that can be represented like this, because this is a positive angle here, this is the amplitude, and Im angle minus theta can be represented like this. Im is the length and minus theta is the angle. So in this way we can represent different signals we have in a circuit and what are the relationships between them in terms of phase, in terms of amplitude. All of those things can be represented in one graph here. This is called phasor diagram. Another very important thing, if we want to represent a time domain signal into their phasor domain quantity, then we can do something like this, right? So Vm cos omega t plus phi is equal to Vm angle phi. Very simple, no problem. But let us say if we have something like this, Vm sin omega t plus phi, then what to do? Because we know in our complex exponential, the real portion was cos signal, not a sine signal, but here we are seeing the sine signal. So first of all, before moving on to the phasor domain, we have to first convert this into its cos value. So that is what done here. So if I just convert that into its cos value, then this should be something like this: Vm cos omega t plus phi minus 90 degree. So when we convert this sine into cos, we will have to add this minus 90 degree. As a result, we are seeing the phasor domain representation here is Vm angle is theta minus 90 degree, this portion, right? So in this way we can actually convert a time domain signal into its phasor domain quantity. Now previously, when we discussed in the previous lecture, we said that one of the problems we had in solving AC circuits was to calculate differential equations. So to calculate derivative and integrals, these are very difficult when you have different multiple elements in the circuits. All of them are AC quantities. So can we actually solve that problem using phasor? Let us try to look at this one. So we are trying to find the derivative and integral in phasor. So just like before, we have this signal, the voltage signal V of t, which is Vm cos omega t plus phi, and this can be represented in terms of its phasor, which is this one. Here this bold V is actually the phasor of our sinusoid V of t. This can be represented as Vm and the angle is phi, right? This is the phasor counterpart of our signal V of t. Now, if we want to find the derivative of V of t, that should be something like this. Obviously, we had already seen in our previous video how to take the derivative of V of t. So that is this one, right? Now, again, we have to take the cos version of this sine signal that is done here. Because we have minus sine theta here, minus sine theta is equal to actually cos theta plus 90. That's why we have written it like this. And then we can take the complex exponential of that. So this is the complex exponential, and we are just taking the real portion of that for converting this one into the phasor form. And finally we can take this value e to the power j90. This can be written as cos 90 plus j sin 90. Now cos 90, this value is equal to 0, and sine 90 is equal to 1. So we can write 1 here. So this total value, this is equal to j. That is what we have done here. Omitting this portion, we have just put this j value here, and all the other things are kept as before. So finally we get this equation, and this particular portion here, Vm e to the power j theta, we had already seen this is the phasor of v of t, which is this one, right? So we have finally simplified this one. Now what we are seeing, actually we are seeing that to find the derivative of a signal in the phasor domain, we just multiply this thing with j omega, right? That is what we have done here. V of t, its phasor is v, and after calculation we have found out that d dt of v, the phasor of this thing is actually j omega v, right? So that is what we have learned here. And in the similar way, we will see that if we take the integral of v of t, the phasor domain representation of that will be just division by j omega. So very simple. We have simplified the whole process into some formulas here. So based on this observation, what we have learned that taking this phasor of a time domain quantity has some benefits. The first benefit is that the derivative and the integral in phasor domain is simply just multiplication with j omega and division by j omega respectively. So our complicated differential equations can be solved easily now. Another benefit is that when you sum two sinusoids of the same frequency, it also has some easier process. We will see that in the next slide with some example. But the problem is when we calculate these things, all the sinusoids we have in the circuits, they have to have the same frequency, right? If they don't have the same frequency, then taking the phasors won't be easy. It will be difficult, right? So we can apply these things only when we have signals with same frequency. Now let us try to look at this second benefit we had discussed earlier. Okay, so here you can see we have this problem where we have two different sinusoids, the current I1, this one, and current I2, this one. We have to find their sum. To find their sum, first of all, we have to convert them into their phasor domain quantities. So we have done that. I1 is equal to this one. We will just take the amplitude here as the modulus and the phase as the argument here for I1. And for I2 also, this is a sine signal. That's why we have to convert that into its cos value. That's why we have added this minus 90 degree. Finally, we get this value. So its phasor domain quantity is 5, angle is minus 110 degree. Okay, and now we can actually add this up, right? As we had earlier discussed, when we get different sinusoids in the problem, first of all we will convert those into their phasor form, then we will do all the calculation. Finally, when we get the value, the phasor final phasor value we want, we can convert that into again to the time domain quantity. So now after getting these two phasor values, we are just going to add them up. So this is what we are doing. We are just going to add them up. These are the polar forms. For simplicity, we are going to convert those into their rectangular form. That is what we have done. We have added all of them up. Then finally again converted those into their polar form so that it is easier to convert them into their time domain quantity. So finally, this is the phasor value we are getting. This is the result we want, but in the time domain form. That is why we have converted that into its time domain form. So we have taken the amplitude here, this one, cos, obviously it should be a cos signal, omega t minus this phase value, right? In this way. So very simple to understand, but you see the whole addition process or summing process has become much simpler because of taking the phasor. Previously, if we had two cos signals like this or two sinusoids like this, adding them use different formulas, right? But here we have simply calculated that using the phasors. So this is the second benefit we discussed earlier of phasors. Now, so far we have represented voltage or current, this kind of time domain quantities into its phasor domain quantity. But what about resistor or capacitor or inductor? What can we do about those? That is what we are going to see right now. So we need to find out the relationship between the voltage and current for each elements. Let's say for resistor, what is the relationship between the voltage across that resistor and the current going through that resistor in terms of phasor domain representation. So let us try to understand that. So here, as you can see, we have this simple circuit here. So we are just taking the portion where we have this resistor, and this is the voltage V across this resistor. This is the current going through that, and all of these are represented in terms of their time domain quantities. And this is actually their phasor domain representation. This is the phasor voltage, this is the phasor current, and this is the value of resistance. So how to actually make a relationship between this phasor voltage and phasor current of this resistor? So let us assume that the voltage we are supplying across our resistor is Vm cos omega t plus phi, and this can be represented in its phasor form like this. Vm angle is phi, and let us call that V. Now, taking the help of Ohm's law, we can represent the current going through that resistor like this, just dividing by its resistor R, right? Now this thing can be represented in its phasor form like this. So this is the amplitude as modulus, and this is the phase taken as the argument. So this is the value of phasor I. If we compare these two equations, we will see that V is equal to IR. So phasor V and the phasor I has this kind of relationship, exactly like your Ohm's law in time domain quantity. So very simple, but generally what we do, we can also represent this behavior of resistor in terms of its phasor diagram. So if we say phi is the angle, then this is the angle we are getting, and this is the amplitude for V, right? So this is the phasor V, and I has the same phase as its voltage quantity. That's why it is in the same direction but with a different amplitude, Vm by R, right? So this length here is actually Vm divided by R, and this length here this is actually Vm. So their amplitude is different, but they have the same phase. As we had discussed earlier in the previous video also, we had seen that for resistor, the voltage and current both has same phase, but they may have different amplitude based on the value of resistor, right? So that is the relationship of voltage and current for resistor. Now let us try to do the same thing for capacitor also. So we have similar kind of circuit with capacitor. V is the voltage applied across our capacitor, and I is the current going through our capacitor, and these are just time domain quantities. The phasor domain quantities can be written like this. Now the voltage we are applying is V of t, which is Vm cos omega t plus phi, just like before, and the phasor quantity of that is this one. But if we want to find out the value of current, we have to take this particular expression, I is equal to C d dt of V. We had already seen that in our previous video. Let us try to calculate that, and if we take the derivative, we will get this kind of expression. But we have to convert the sine signal into its cos counterparts, because we want to represent that into its phasor form, right? So we have to first find out the complex exponential. So that is why we have converted into its cos form, and finally we have written the complex exponential here. And this term here is actually giving this particular exponential portion. We know this portion is equal to j, that is written here, and we have this final expression here. And the portion here we are seeing, except the time portion, is the phasor of the current, which is this one, right? And this particular portion here is actually this, right? So if we just compare this one with this one, we are going to get this particular expression here. Okay, so from this one and this one, we are getting j omega c v is equal to I. This is the relationship between voltage and current for a capacitor, right? Now if we want to represent this relationship in terms of a phasor diagram, how should that look like? Obviously it should look like something like this. So here you see the current of the capacitor is leading the voltage by 90 degree. As you can see, the current IT, the expression here has plus 90 phase here. So obviously the current of the capacitor will lead its voltage by 90 degree. That is why we have this J term here. So that is what happening here. So we have to always remember, for a pure capacitor, the current should lead the voltage by 90 degree, exactly 90 degree. Now let us try to do the same thing again for inductor. I don't want to explain everything how this is coming out, very simple to understand, but if you calculate everything for the inductor, you will see that we are going to get this expression right here. This is the relationship of voltage and current for inductor. And if we want to represent the phasor diagram, we will see that, you know, current is actually lagging the voltage by 90 degree. So voltage is ahead of current, because here in this derivation we started with current, and the voltage here, voltage is actually leading by 90 degree. As a result, we have this phasor diagram and we have this J term here. So obviously voltage will lead the current by 90 degree for inductor. So that is the difference between capacitor and inductor in terms of their phase. Now the final thing, based on this relationship we have, we want to represent each of the elements we have, like resistors or inductors or capacitors, by a fixed value, and that is done something like this. So previously we had seen this voltage and current relationship for resistor, capacitor and inductor. So all of them can be represented in terms of voltage divided by its current, which is coming from, you know, Ohm's law. So always we are saying that the resistive property of an element can be represented by the voltage across that element and current going through that element. So that is what we are trying to do here. This is exactly your Ohm's law. So using that Ohm's law, or taking the help from Ohm's law, we can also represent the resistive property of other elements like capacitor or inductor in phasor domain. So that is what done here. So if you take the voltage divided by current for capacitor, the value is this 1 divided by j omega c, and for inductor this is j omega l. This particular quantity, the voltage divided by its current, and this thing is written Z, and this is called impedance. So this is the generalized term we are going to use to represent the resistive property of all the elements, resistor, capacitor or inductor, in AC circuit analysis. So now the general definition of impedance is, it is a frequency dependent quantity that represents the opposition that the circuit exhibits to the flow of sinusoidal current. Okay, so obviously it will resist or oppose the flow of current. That's why we are saying this is resistive like property, but the term we are going to use to represent here is called impedance. Now based on those, let us try to generalize everything. Like for R, L and C, we have different value of impedance here, and you know, only for the resistor the value of impedance is real. For inductor and capacitor the value is imaginary, right? Now another thing to note here for impedance of capacitor is that it is written something like this: Z is equal to 1 divided by j omega c. This thing can also be represented as minus j divided by omega c, because earlier we had learned that 1 by j can be written as minus j. So this can be also written as this particular value here. So impedance can also have negative values. And another thing we can also note is that for resistor, when we have different value of omega or different frequency, then the value of resistance is not changing, right? The value of impedance is fixed. But for L or C, what is happening? This is a frequency dependent quantity. As a result, when we have omega value of 0 for this one, we are going to get 0 impedance. And when we have infinite amount of frequency, then we are going to get impedance of infinite for the case of inductor. For the capacitor, it will be other way around. So we will see that when we have omega is equal to 0, then we will have infinite amount of impedance, because the impedance and the frequency are inversely proportional. And when we have infinite amount of frequency, we will have 0 amount of impedance. So these things has to be remembered for our calculations. Now finally, we have another term called reactance. So what is reactance? There can be situations when we will have different elements interconnected with each other, like different resistors, different capacitors, different inductors interconnected with each other, and they can have an equivalent impedance, the total impedance of the whole circuit. For those cases, we can represent the total impedance something like this. So R plus jx, this is the real portion and this is the imaginary portion. The real portion is the resistance, obviously, and the imaginary portion we get is actually called reactance. So it can be because of inductor, it can be because of capacitor, or it can be because of both. So we can have different amount of inductors and capacitors interconnected with each other, and as a result, what is happening? The reactance value x can be positive or negative, because we said this impedance of capacitor can be represented like this. So impedance can have negative value. So if in a circuit it has more capacitance than inductance, obviously the value of reactance x will be negative. And generally what we say, when we have value of x as positive, we say that impedance is inductive, and when we have negative value of x, we say the circuit is capacitive, because negative value comes from this capacitor, positive value is coming from this inductor, that is why. And finally, just like your resistor, to represent impedance, reactance, anything, we are going to use the same symbol ohm. Okay. And finally, for simplification, we can also represent that in terms of its polar form, something like this. This is also possible. So whenever we need in our circuit analysis, we can represent this value of impedance in terms of its rectangular form, its polar form, no problem. But finally, when we get the results, then the voltage or current quantity, these things has to be written in terms of their time domain version. That is the only requirement we have here. But you see, finally, because of this impedance and reactance, this kind of quantities, we can represent all the possible quantities we have in a AC circuit, like voltage, current, resistance, impedance, reactance. All of these things can be represented in terms of its phasor quantity, right? All of them can be represented in a phasor diagram. This is possible, and it can be solved without calculating any differential equations. So these are just some of the concepts we need to understand to solve AC circuits, but later on we are going to solve some AC circuits to understand how these things are used. That's all for this lecture. Thank you.